Right, welcome everyone to the ATN seminar today. Our speaker is Mathieu Carrière, who will be talking about diffeomorphic interpolation for efficient persistence-based topological optimization. Take it away.
All right, thanks a lot. Great pleasure, of course, to be able to discuss this project that my co-authors, Mark and Theo and myself have been working on recently, which has to do with, as the title says, topological optimization, right? So we more or less got a bit deeper into what can be done and achieved, both in terms of, let's say, a little bit on theory, but mostly in terms of practical efficiency concerning topological optimization, right? So I guess I'll start with, first thing first, the basic concepts. So I'm sure many of you are already familiar with those notions, but I'll explain them quickly anyway, at least for fixing the notation. So topological optimization for me is going to be actually optimization of persistence diagrams, right? So the optimization of persistent homology, right? And in this talk, even though persistent homology can be applied on several types of objects, structured objects like graphs and triangulations, I will also mostly focus on point clouds, actually, persistent homology computed out of point clouds, right? So just as a quick reminder, the way we actually generate those so-called persistence diagram is through a filtration that can turn these objects, X, so this point cloud in particular, into another point cloud, but this time in R2, called the persistence diagram. And you do this with a filtration of X, a sequence of nested subspaces. And as for, many filtrations possibilities exist for point clouds, but one of the most famous one is, I'm sure most of you know, the Xesh filtration and the Vietoris strips filtration. So you can see the Vietoris strips as an approximation of the Xesh. And basically, they amount to growing spheres around the point, right? Or equivalently looking at the sublevel sets of the distance to the point cloud function, right? And then storing in a persistence diagram the radii of the sphere at which cycles appear or disappear, right? So depending on the radius that I use for the spheres around the points, I might create cycles or not. Every time something appears, I start a bar in the barcode and I stop it when the cycle disappears. And the starting and the stopping values will be the coordinates of a single point in the plane. And this is how I get my persistence diagram, right? And it captures homology in, it's a way to capture the homology of the underlying object, but at, multiple scales. Again, with the interpretation that points close to the diagonal are usually associated to noise in the data, right? Because we don't know the underlying shape. We only have access to a sampling. There might be active artifacts because of that. Usually, those correspond to points close to the diagonal. All right, so there's been some work, some recent work, at least during the few past years, people have been looking at how to actually incorporate those objects, the persistence diagrams, these topological descriptors, into losses, for instance, when you want to regularize a machine learning classifier, right? This is an example of topological optimization where, in general, you're interested in running gradient descent, okay, on an, let's say, an objective function that depends on the persistence diagram. And there's actually, it's not so complicated. The first thing you need, the one and only thing you need to know to be able to do this, at least naively, is to recall that, as I said, if you pick any point in this persistence diagram, its coordinates will be the filtration value of some positive and negative simplices, right? The positive simplex, or in the case of point clouds, the positive critical point being the points that make the cycle appear, and the negative one being the points that make the cycle disappear. Okay, so that only means that, for instance, if you're interested in the gradient of a persistence diagram with respect to the filtration, well, if you pick any point P in the persistence diagram, the gradient of P will just be the gradient of the filtration itself applied on the positive and negative simplices. Okay, and that interns means that if you want to run gradient descent, the only thing you need to know or to have access to is a function giving you, for every point in your persistence diagram, the critical points in your point cloud associated to it. Okay, that's an example, for instance, in the RIPS filtration. So here you can see the little spheres that I grow on the points. Okay, so for this radius, for instance, I'm going to draw an edge between points as soon as their corresponding sphere intersects. And for instance, for this radius, I create this edge, which is the last one that I needed to create this cycle. So this radius of the sphere is, if you want, the x coordinates of the point in the persistence diagram representing this cycle. And on the other hand, if you increase more, then you will also at some point completely fill the cycle with triangles. And the radius for which the cycle is completely filled will be the y coordinate, the depth time of the point in the persistence diagram. Okay. And here I'm writing dxa, xi, and dxk, xl, because the value of those edges, or the radius of the sphere, well, up to a factor 2 is a distance between the points. Okay. So based on that, you can even continue and define the gradient of the persistence diagram with respect to the points of the point cloud themselves, just by computing the gradient of the distance between two points with respect to the point coordinates, right? Which is super easy. It's a simple linear algebra. So that's more or less, roughly speaking, how people have been using gradient descent so far, using topology. Theoretically, it's not so easy to analyze because the space of persistent diagrams is a bit particular. Okay, it's not a vector space, but still, this way, just using the critical simplices, give you a direct computational tool to perform a gradient descent. It's challenging, but still some theory can be written. And as I was saying, there are many applications, but one of them is the regularization of models. Okay, so for instance, forcing some machine learning models to satisfy some topological priors on the data. And we'll see an example of this a little bit later in the talk. One also little observation is that, as some of you know, computing like SESH or RIPS persistence diagram can be a bit computationally expensive, right? Especially on very large point clouds. So it's kind of frequent to subsample the data first, right? Compute the persistence diagram on the subsample and use the gradient of the subsample to update the points in X itself. Okay, it's kind of an almost trivial observation, but this is something that will be interesting later on for the tool I will present next. All right, this is just a small example of point cloud optimization, right? Here, for instance, this is a toy example where I started with point clouds in random position in the unit square, sorry. And then my objective function was the total persistence of the various RIPS persistence diagram. And if you try to minimize this, which means, maximize this, try to push all the points away from the diagonal, all the points of the persistence diagram away from the diagonal, intuitively try to maximize the sizes of the cycles in the point cloud, with some constraint that the points have to stay in the unit square, otherwise the cycle can increase infinitely. Well, this is what you get. This is an example of local minimum of topological optimization, okay, on the point cloud using the address RIPS. All right. Okay, so that being said, few, I guess, problems or weaknesses or issues, I guess, with this way of doing optimization have been, noted by the community. One of them is, obvious from how this vanilla gradient, so vanilla means, the method I just presented, the way these gradients are computed, make the gradients quite sparse, right? Because as I said, the gradient only depends on the critical points. So in the case of Vietor's RIPS, because the filtration value are given by the distance between two data points, every point in the persistence diagram has an effect on at most 4 points in the point cloud. Okay, so lots of coordinates of the gradient. If you imagine the gradient as, you know, the gradient of the persistence diagram with respect to all the points, this vector will be mostly zeros, you know, and will be one non-zero at the critical points. Plus, and this is, I guess, another kind of problem, but the gradient itself is defined on the points of x, right? Some critical points of x. In practice, that means that assuming you have optimized some point cloud, okay, some coming from somewhere, and then you get access to new data points, right? If you try to apply the sequence of gradient that you computed through gradient descent to these new points, well, with probability 1, it will have no effect, because with probability 1, your new data point will not be exactly on one of the critical points that you had at the beginning, and it will not be moved or touched by the sequence of gradients, okay? So this is something we actually wanted to, you know, to correct, or to find ways to deal with this, okay? To be able to apply a topological optimization process, to compute it once and for all, and then to be able to apply it on new data points, okay? And I also, okay, I guess in terms of computational efficiency, what I mean here with the poor interplay with subsampling is that it will even slow, if you use subsampling to, you know, make the persistence diagram computation fast, you won't improve on sparsity. Like the gradient was sparse, but if you apply it on a sparse subsample, it would be even worse. Okay, so that's what I mean by poor interplay. And here's the, yeah, kind of an illustration of this. I have this point cloud given by blue points. I first subsample it with red points. And as you can tell, like the black arrows are the one given by my gradient, the gradient of this loss, right, the total persistence. And, you know, except on, all right, 4 or 5 points, it's 0, okay? Which make optimization slow and not super efficient. Plus, for those of you who know, topological optimization can also be sometimes a bit erratic, because those critical points, they're very unstable. Like if you slightly change the filtration, the critical simplices can be really, can switch from some critical point somewhere to some other critical points located like very far away. All right, so, and here's one application of where it would be useful. There's this thing of being able to apply a sequence of topological optimization, well, to be able to apply topological optimization on new data points. It could be useful, for instance, in principle on, let's say, dimension reduction, but also generative models, variational autoencoders, for those who know. So let me just explain the task a little bit, and that we will use as a kind of a motivation for the trick. We'll get some data that will first pass to some encoder network that will map the data in 2D, okay, 2D space. And then we'll have another part of the network, the decoder, that will map it to, you know, to its original space. But what those kind of models allow, for instance, is once you have a latent space, you can sample a new point in that latent space and decode it to generate a new image. Okay. So there are some data sets, and we'll see one where you can also impose some topological prior. And for instance, in the data set that I think I'll, maybe, is it? No, okay, that I'll present in the end. There's a prior, the data should be on a circle, because you will see the data will be based on images rotated around the same object. So it makes sense to ask, or to try to make the latent space as close as a circle as possible. Okay, so you could do that with topological optimization, as I was presented before. But if now you want to be able to sample from that circle in order to generate a new image, because you have a new observation, then you'll need a way. Well, you could always, of course, recompute and redo the topological optimization, but you don't want to do it every time you have a new observation, right? So in practice, ideally speaking, you would like to be able to apply topological optimization without having to recompute everything all the time, every time you have a new point. So you need more or less to extend the sequence of gradients to the whole latent space instead of just the critical points. Okay, and yeah, I guess it will be a bit more clear once we see the data. But this thing of modifying the latent space so that it looks like a circle also allows for better interpretation or an easier way or more intuitive way to generate generating points for data generation. All right, and you don't also we also don't want to do that during or to decouple, let's say, the training of the VAE and the topological optimization. Ideally, we also want, for instance, someone giving me some already trained model, okay, with some latent space. Then I fix it with topological optimization without having to touch at the model itself. Okay, for me, I will treat it as a black box. Okay, so you can also see this as a way to more or less correct the model so that the latent space matches a bit better the topological prior that we have on the data. And this is different to topological regularization, or what is called topological regularization, which imposes this topological prior at training time, right? There's a like kind of big line of work or trend or like series of paper which study what happens if when you learn or train the model, what happens if you impose at training time the topological prior. Here, I'm assuming the model has been trained and I will treat it as a black box and then apply topological optimization. All right. So in order to handle these questions or to answer these questions, we used some trick that's actually known in geometric data analysis, basically diffeomorphic interpolation, which basically solves the problem of finding a diffeomorphism, or if you prefer, a vector field defined on the whole space. Okay, so it's a function going from the space of data points RD to RD, not only on the critical points, and that interpolates the gradient of the loss. Okay, I want that on the critical points, my vector field matches. I want it to match the gradient. Okay, with the gradient, with L being some loss. Okay, for instance, this could be a loss forcing the persistence diagram of my latent space to be looking like the persistence diagram of a circular space. Okay, so one way to, I guess, get a solution to this, because you can think there are obviously many vector fields that satisfy this constraint. I can look for one with minimal norm. Okay, so I can look for vector fields V in, for instance, some reproducing kernel Hilbert space. Okay, which is kinds of spaces that are quite famous among data scientists. Okay, I won't explain exactly how it works. Just remember it's a Hilbert space of vector fields. Okay, with some interesting property. Well, at least you can think of it as a constrained space. Okay, I won't look for any vector field, but the one belonging to the RKHS of a Gaussian kernel. Okay, and in this field, I would look for the vector field with minimal norm. Okay, or if you prefer, the projection of 0 onto the vector fields that satisfy the interpolation constraint. The nice thing about looking for fields in these RKHS spaces is that it has a closed form solution. Okay, the one with minimal norm you can prove is equal to, well, this equation. Okay, so where this K here is a big block matrix. You see, it's the Gaussian kernel but extended to a diagonal matrix, and then this K is some sort of big block matrix formed by all these diagonal matrices that I have to invert. Okay, and then apply the kernel itself on it. So I guess one way to understanding it, instead of going through every term in this equation, you can really understand this as taking the gradient of the loss, the vanilla gradient, the one on the critical points, but then smoothing it by convolving with the Gaussian kernel. Okay, and then this K minus 1 gradient is, if you want, some extra term that you input that you multiply with, so that the constraint is respected, so that you match the gradient on the critical point. Okay. I guess one issue with this formula is that you have to invert a potentially large block matrix, right? Because you see that here K can, the way it's computed, see, you have one block matrix for every pair of critical points. Well, fortunately, as I said before, the set of critical points is sparse. So I guess the size of K is a bit mitigated by that. Still, it can sometimes lead to numerical errors, right? Because if the matrix still is not super well conditioned, inverting it becomes difficult, and you might have sometimes from an iteration to the next some kind of weird looking vector fields. But in practice, when we applied it, we didn't notice that much. So it wasn't that bad. And obviously, given that now we have a vector field defined on a whole space, here's the nice thing. If you give me a new observation, obviously, then I can apply the vector field on it. And this is an illustration of that, right? Here I have, again, a blue point cloud, okay? And I'm trying to push the point of the persistence diagram that's far from the diagonal. I'm trying to push it towards the diagonal. So trying to destroy the circle. So the vanilla way, okay, you will look at the 4 points, the 4 critical points of the point cloud. So those 2 which are responsible for the creation of the cycle, okay, and those 2 which are responsible for the filling of the cycle. And I will move the positive critical points away from each other and the negative points closer to each other. Okay. Well, if now I extend that with a diffeomorphism, you see that the support of the vector field is now a bit bigger. I'm more or less convolving this with a Gaussian kernel. So now I move much more points at the same time. And here's what gradient descent looks like based on that, right? You take your initial point cloud. Then, if needed, if it's too big, you can subsample. And here's also the nice thing about using these vector fields, is that if you subsample, that's okay, because you can still extend the gradient of the subsampling to the whole space itself. So even if you subsample, you can still move a lot of points at the same time, okay? So now I guess this is a way to say that the interplay with subsampling is a bit better now. You compute the gradients, possibly on the subsample, extend by diffeomorphism, and then update. Okay, and if you get a new observation, that's okay. You can just apply the vector field or the sequence of little vector fields, the sequence of small diffeomorphism. You can apply it on any new point and get the image of the new point by this flow, actually, right? This sequence of diffeomorphism can actually be also understood as kind of a discrete flow of the topological gradient. We realized it was actually hard to prove many things with this method. We tried though, but at least we get to the point where we could show that this vector field at least gives the descent direction, okay? Showing that it makes sense. You won't increase the loss by applying the vector field. Plus, you also have some control over its smoothness, like its Lipschitz constant. Okay, so how different is the application of the vector field for 2 close points? Definition of the Lipschitz constant. We could bound this by a few terms that depended, for instance, on, as you can guess or intuitively guess, the bandwidth of the Gaussian kernel, right? If you have a big bandwidth, you're impacting more points, but also the condition number of the block matrix. Okay, if the matrix is really badly conditioned, it's harder to control the smoothness of the vector field because you're more prone intuitively to numerical errors. Okay, but we're still investigating what else we could do as of like theoretical analysis of this vector field. We have some ideas, but we still have to get to that point. All right, so here's now the illustration of what happens if I solve or optimize the same data set as before. Again, I'm taking these blue data points and I'm trying to kill the circle. Okay, so in orange you see the vector field of the subsampling data set. So the red points are the subsample points. The black arrows are the vanilla subsample, and in orange, the extended gradient. Right. on the right here, you see what's the effect of diffeomorphic interpolation. Okay, so you see that now it's funny to see that vanilla and diffeomorphism converge to different minima. In the vanilla gradient descent, you will more or less try to move some points inside the circle, because for those of you who know, the RIPS filtration is quite sensitive to outliers, right? So it's enough to push a few points inside to completely destroy or to mess up the persistence diagram. Here with diffeomorphism, well, it looks more like the action of a diffeomorphism, right? It looks more like you're smoothly crushing the circle itself in order to reduce the size of the circle. So a way to interpret that the point of the persistence diagram here is close to the diagonal is that now you're getting to a point where the appearing or the positive points are there. So this would be more or less the positive radius responsible for the creation of the circle. And it's getting closer and closer to the killing radius, right? Which would be something like this, for instance. Okay. So even though there seems to be some sort of, well, we still see some circle, we're also at the same time making the positive radius closer to the negative radius. So still, this is a way to show that the topological loss is indeed optimized.
Matthew, can I make a quick?
Yeah. Yes, of course.
Quick comment here.
Mm-hmm.
In this deformation one, or the diffeomorphism one, I'd be interested what happened if you reduced the noise a little bit, but still kept enough noise to break symmetry. Because there's some questions in metric geometry, like what's the best way to fill a hole, and sometimes people conjecture that you get this like threefold symmetry, which you're sort of seeing here. So I'd be
that's interesting. Okay,
I'd be interested to see what happened as you reduced noise. You know, if a clean thing comes up.
Okay, so like you mean here, instead of adding some uniform noise around the points, I just sample exactly on the circle and I see what happens. Yeah. That would be cool actually to notice if this kind of branching or Y shape can actually be interpreted some way, somehow. That could be for sure. That would be interesting. Yeah.
Thanks. Yeah.
Maybe one point also that I forgot to mention, and that some of you might wonder about, you know, that given that, you know, a diffeomorphism is smooth, you can never change the topology of a space by applying a diffeomorphism on it. Still here, by optimizing the persistence diagram, we're still creating to change the topology. So it might seem, you know, contradictory. But if you want, even if what you compute is a diffeomorphism, the fact that you just have a sampling, not the space itself, allows for, you know, creation and destruction of cycles. So if you want, that's kind of what compensates the fact that we have a smooth gradient. Yeah, and then we play the same game, this time on a bunny, okay, the Stanford bunny. A bigger point cloud, okay. This time we try to maximize the H2, okay. So it's like this is a surface, okay, homeomorphic to a sphere. So we try to increase the cavity. What's interesting to notice on this example is that it has more points than the example above, which makes it harder for vanilla optimization. Not impossible necessarily, but harder. So either you compute the persistence diagram of the whole point cloud, but with 36,000 points, well, it's not impossible again, but might be a bit long, or you subsample, but at the same time, given that the object is quite big, sometimes even the subsample, I mean, if your subsample is too small, let's say, you don't have enough points to capture the sphere itself, the topology itself. So that's what illustrated here. We took a subsample so that optimization runs, you know, takes not so much of a long time, but at the same time, the subsampling was too small. The diagram couldn't capture the H2. Whereas, you know, if you apply the same subsample with really a few points, but then extend it with diffeomorphism, yeah, after a few steps, well, you get what you want, okay, a bunny map to a sphere. Yeah, what's important to notice is that we use the same subsampling size for both, okay? So that the gradient optimization can be computed fast because it's a small subsample, but vanilla wouldn't work because you don't have enough samples to capture properly homology. Right, and then back to the decoder VAE example that I hinted at the beginning. So now you might guess why this topological optimization could be useful, because if I'm taking now a trained variational autoencoder with some fixed black box encoder and decoder, if it's a black box, I cannot touch its parameters, right? But still, given that now I have a flow, let's say, a sequence of diffeomorphism, I can still apply it on the latent space, okay? I can take my black box model, get a latent space, with some diffeomorphic interpolation, well, gradient descent, get to a circle. But even better, I can also revert that flow, and from the topologically optimized latent space, get back to the original space. Okay, and that's actually interesting, because if I just did optimization with phi, okay, I get this nice circular latent space. But then if I pick any point in the latent space, like the purple one, and if I apply the decoder on it, maybe it wouldn't work, because maybe this circle is actually far from the original latent space. And because it's far from it, really in terms of 2D coordinates, it could be that the circle is, like, for instance, much bigger, like this. So we're outside of the functioning regime of the decoder. So we would create an image, but which doesn't look like anything, doesn't look good. Other way around, I can just sample from it and then just push it back to the functioning, like, regime of the decoder and decode it into a nice looking image. Now, in terms of interpretation, if you have a good reason to assume that your data should be circular, then that means that it's easier to sample from this circle with an angle, for instance, if you want to generate some new data. Maybe it will be more clear when I show you the data sets. Let me just see if I forgot something. No, yeah. So for instance, here it is, right? We have some data sets like this one. So every object is its own data set. And every data set is this object, but rotated, okay? That's why you would assume it's fair to assume the latent space should look like a circle. Okay, so now let's say you want to generate new images, okay, on some angles that you have not observed in the latent space. Well, if you try to do it directly, it might be not so easy, right? In orange here, you see what the latent space of a pre-trained black box VAE looks like, okay? So actually, it's a closed curve, okay? You have to imagine orange points here crossing here this line, but it's fine. It's not so bad because it's a curve, okay? It's a one-dimensional, more or less, manifold, one-dimensional curve. But if you just give me an angle that I haven't observed, it's hard to see where this angle would be in that orange, linear data set, or not linear, but a one-dimensional data set. Reciprocally, I can do what I said, just extend it to a circular space. So that's the blue one. Then if I'm missing an angle, then it's easier to see where this angle will be on that circular looking shape. For instance, here, let's say I don't have the image corresponding to that angle. And then, as I was saying, in green, I will push it back to the orange space, the functioning regime of the decoder, and create a corresponding image. It's not super easy to see, but if you look closely at those two images, you'll see that, and sorry, this image here is the one that I get after applying the decoder directly on the blue space. And maybe some of you can tell the image is not super clean. It's way cleaner once you apply it there on the origin space, which again makes sense because that's, again, functioning regime. And this way I can just sample directly with angles, okay? Not with this. I don't have to use this kind of weird and model-specific parameterization of the data. I can just use the circular one, okay? And again, I can do that for actually any model, right? Given that I'm treating those models as black boxes, this is a technique that could be working on any architecture, right? I'm not making any specific assumption about the model itself. So here we're showing what the results looks like for a few others. Note that it's not perfect at all, right? Like for instance, you can tell here or here that the parameterization is not always super great, okay? We also have some other examples where there are other types of collapses like this, okay? So we're still kind of trying to understand and fixing some those bad cases and those bad scenarios, but right, you get the idea. All right, a few things to say before I conclude. So the take-home message is this one, right? We're trying to fix this sparsity and kind of computational efficiency and extension of gradients that are problems that you get with the vanilla gradients, and we fixed it by interpolating, creating a new vector field defined on the whole space and using it instead of the gradients. Again, that's a nice, it also has a nice interplay with subsampling. If you want, you get both, you get the best of both worlds. You can subsample to compute the diagram super fast and then extend it to still have an optimization that also goes fast. Okay. Note also that we're not the only ones that have looked at those limitations of vanilla gradients. There are other extensions, either, I guess, more from a mathematical point of view, like extending the gradients in a gradient sampling way by using the stratification of the data induced by the filtration. Okay, in this approach, you get a better control of the rate of convergence of the gradient optimization process. Or there is also this nice approach by Dmitry Morozov and Arne Nigmetov about optimizing with big steps, which means every time you have, more or less intuitively, every time you have critical points, like let's say you're at a given iteration of your gradient descent process, right? You have some critical points and critical simplices. You can look at all the simplices that are, if you want, associated to those critical simplices. The ones that you would need to also move if you were to move the critical simplices some way in the filtration. And then find them and then optimize them directly instead of only the critical simplices. So that's what they call the big steps. Okay, so it's an approach that also kind of a bit similar to the one I presented, although it also has a few differences. Let's say, for instance, that it doesn't, as far as I understand, has the same effect with subsampling. Like you could still apply big step of subsampling, but you still have the problem that this big step gradient still are, the subsampling, for instance, is too small to capture the whole topology, right? Plus, I think this is a unique property also, the fact that these diffeomorphisms that we get, as I said, can be just computed once and for all, right? Once you have it, you can apply it without any additional computation. Whereas if I play the same game as before, I give you a new observation, even if you use big step gradients, for a new point, you might have to recompute those gradients again if you want to see where that point goes, or after optimization, okay? So those are the nice, I guess, things. Also the weaknesses of that is, as I said, we don't have, for now, so many guarantees about this vector field. We're looking, for instance, on whether we could quantify the rate of convergence of this gradient optimization, diffeomorphic gradient optimization. Turns out that it's actually not super easy. We're also thinking about extensions, like diffeomorphic interpolation that would work even outside of the range of point clouds, like for other types of structured objects. If you look at how it's defined, what's important is more or less to have a well-defined kernel on your data space, okay? For points on a point cloud, it's easy because many kernels exist. Now, if you get, for instance, nodes in a graph, there are also some graph kernels that could be used for that task, okay? But this is something we're investigating. And I guess a bit more practically speaking, I haven't discussed also that much how you could choose or tune, for instance, the hyperparameters, the bandwidth of the kernel itself. This we had to do kind of quite heuristic way, okay? So we're using techniques that are known in data science, like for instance, picking a power of the median of the pairwise distances of the points in the data set, tricks that people have been using, a lot in data processing. It would be interesting to see whether we could get also some more precise tuning or even more generally, some kind of adaptive way, right? Whether it would be possible to get a kernel first that we could tune automatically, and on which also the bandwidth could adapt to the point cloud, okay? Because it makes sense also to assume that if your point cloud really changes, right, has a new shape, right, the distribution of pairwise distances will also be very different. So it's very likely that a good bandwidth for the kernel is going to change as well. So how to adapt the kernel with respect to the iteration is also some interesting question that we're thinking about. Okay, and that's still open for us as of today. All right, so I think, yep, that being said, I thank you for your attention, and if you have any question, I'll be happy to take them. Thank you.
Thank you very much, Mathieu. That was really excellent and exciting. Let's all unmute briefly and clap.
Thank you.
All right, so let's see. I don't think there are any questions in the chat at the moment. So while people are waiting to formulate their questions, maybe let me start with one. Namely, it seems to me, I mean, it's obviously, I think it's the right way to solve this problem. But I'm wondering, is this what's the feasibility for this if you actually do some persistence-based optimization now using this vector field approach? Do you think does this
in terms of like numbers or how well it scales?
Yeah, exactly. Yeah.
All right, so let's see what I can do to that. I think so. So I guess, in the corresponding paper, our way of discussing this was mostly this experiment. This is probably not the. Let's see. Okay, I guess one thing I can say for sure is that we could easily treat bigger pod clouds that what we could with vanilla, just because we're allowed for subsampling. Now, if you don't subsample, it becomes harder actually, because you're computing the diagram itself, and you have this extra step of extending it with this equation here, right? So you also pay the price of inverting a potentially big matrix. I guess in practice, we observed that inverting this extra step that we needed on the gradient itself was, at least in the case of RIPS, well compensated by taking like small subsample. I guess in the end, we could deal with really large point clouds, even bigger than this, by using like very small subsamples, like of the order of a few thousands. But then extending it, which wasn't also too hard because the subsampling was small, which allows to treat like really dense point cloud. Again, at the price also of a little more erratic behavior. Like you see that even though the loss is indeed decreasing, if you take subsamples that are very small, well, okay, you move many points at the same time, but given that the subsampling is a really coarse, sometimes you're not necessarily a super good descent direction. So that's why it also becomes a bit more, can also be a bit erratic if you take small subsample, but at least optimization become feasible even for like let's say hundreds of thousands of points.
Okay, very cool, very exciting. If no one wants to ask a follow-up, I had a follow-up. I'm not sure whether you know the work by Elkanan Solomon and others about these very small subsample Vietoris RIPS complexes. Do you think this could be combined basically to have extremely, how to say that, to have very small subsamples, but many of them, in order to do some kind of optimization at a global scale? Sorry,
that's actually that's an excellent question, actually. Yeah, I think, are you referring to this, because the work I know by Elhanan is he called that is this the one where you take like, let's say, all possible subsets of k points, let's say,
Yes,
and then
exactly.
you more or less average the, definitely. So that's actually one thing we're more or less have in mind at the moment, because we would like to see if the theoretical results that he managed to obtain, because I think he has results on the line of if you use this family of subsample persistence diagram, you have enough to more or less reconstruct the shape or get an isometry up to some constant or something like this. We're actually also trying to see whether this could be helpful in terms of this diffeomorphic analysis, because yes, as you were hinting at, we could play the exact same game. Like we could take the subsample, get the gradients, and more or less smear them in a way by extending them and then combining the vector field themselves, exactly like he proposes actually. We have some hope that this might be easier to analyze, like at least on a theoretical level, than what we're doing right now. Plus, it's also likely that if you combine many subsamples, you would reduce probably this kind of oscillations that we're observing right now, which we get from just one single subsample. So I wouldn't be surprised if this makes the optimization even more, even smoother, let's say. And if we can even, using this, if we can even control a bit more the field or describe the field, like theoretically speaking, that would be great. So that's definitely one exciting future direction.
It's very exciting. Maybe I'm going to have to ping you offline on this, because I think
I'll be happy
an
to.
exciting
Definitely.
Thank you so much.
I'll be glad.
So do we have any other questions in the chat or by the audience?
Well, that's a good question. So in this Stanford bunny example, you're taking the bunny and you're trying to increase the H2, and so you're going towards a more spherical bunny.
Right.
Do you think it's possible to sort of understand the like the global optima of this process, or like the trajectories, or do you think they might be in some sense geodesics?
Oh, you mean like geodesics in the, let's say, the space of point clouds?
Something like this, or space of,
It would be super nice. I guess, so we didn't get to that point, although I might say nonsense, but my intuition on that is you could also try to combine this more or less diffeomorphic approach with all this line of work, trying to, maybe some of you are familiar with this, to really, compute geodesics in shape space with, how do they call that? When you do template registrations or in shape analysis more globally, where you're really computing. Usually, those geodesics are computing with Hamiltonian formulation and integration of ordinary differential equations, but they have the theoretical framework to make sure that they optimize along geodesics in shape space. Here, where basically we took inspiration from that, but only the first step, like creating a vector field out of a given gradient. Now, whether we could interpret this sequence as really a geodesic, that would be super interesting. We tried a little bit, didn't get to that point. I think maybe, as I was saying, it would be a bit hard. Like if your topological objective really tries to change the topology, maybe it might be harder to analyze, because this is something that cannot be achieved with any diffeomorphism, right? Yeah, we're really making use of the discretization or the sampling of the point cloud. So I think in order to make the connection, would probably need to go through, let's say, the analysis of a shape space, but more like of a stratified shape space, like stratified by the different topologies that you're allowing on the underlying space itself. But maybe along these lines, it would be possible to interpret those trajectories as geodesics. Although, to me at least, it's really non-trivial.
Super interesting. Thank you.
Thanks.
Well, so any other questions for the public part of the seminar?
So yeah, maybe I could ask a question. First of all, thank you very much for your talk.
Thanks.
I was wondering, is it possible to have like some sort of more complex optimization goals or optimization functions? So for example, I don't know, we would want to have a lot of very small circles and then a lot of very large circles, but we don't really want medium-sized circles or something. Something
I
like
see.
this.
Yes, I think here that if I understand your question, that shouldn't be that much of a problem. Basically, I guess my answer is if you have a well-defined loss, like a loss applied on the persistence diagram, like for instance, as you said, optimize the points that are far away, the points that are like close to the diagonal, and maybe don't touch the ones in between. As long as you can easily compute the gradient of that loss with respect to the persistence diagram point, then you're good to go, because this part of the work is mostly how to get from a persistence diagram update to a smooth point cloud update, right? So it's kind of the second part of the. So as long as you have a loss that's well defined and differentiable, you should be able to use it in that context.
Yeah. Cool, thank you. So do you have any intuition of whether this would converge to something? Like, I mean, in your examples, the bunny just got blown up, and it's somehow you can see that there's like one ideal shape. But do you think this will always converge? It could be that, I don't know, we'll just end up in chaos.
That's a very good question. Actually, we've tried to match some conditions under which vanilla topological optimization is known to converge. You can prove, for instance, that vanilla here will converge up to, if you choose well the learning rate, if the filtration itself satisfies some like good enough condition. But getting the same results for the extension of the gradients, unfortunately, we didn't manage. So on paper, it was a bit hard to say anything along these lines, although we're still trying. Now, in practice, what I can say empirically is that most of the time, even though the optimum might not look like the optimum of what vanilla topological optimization give you, we did observe some convergence. Like, I don't remember a case where we ended up in some really crazy looking. Well, okay, maybe let me rephrase that a little bit. If you take, for instance, here in that example, learning rate lambda that's really, really large or really, really bad initialization, then maybe in that cases you can end up to an optimum that's really, really hard to interpret. But if you use sensible values, let's say, or reasonable values, even though reasonable is always subject to discussion, we did not observe a lot of like diverging scenarios, even though at the same time we had a hard time proving it. So, but we're still on it.
Well, thank you very much for your answer.
Thank you.
Thanks a lot, everyone. So, any other questions for Mathieu?
Yeah, I do actually.
Great.
Hello, Matthew. Could you go back, or I guess forward one slide?
Yeah.
I guess I had
this one
here.
here.
Yeah, to the experiments.
Yeah. All right.
So what I was wondering is, this is I guess more my ignorance, but when I'm looking at the diagrams here, it looks like the I guess we can call it kind of like the pushes that you made for these deformations are all just sort of like, I don't know if it's like artifacts of the I guess like the Gaussian kernel that you used. And I'm just wondering if I guess if you tried with other kernels, or if you tried maybe with like two topological goals, right? So like instead of separating the sphere or destroying the sphere, just break it up into two, right? Are the moves sort of similar? These sort of like pushes that are like normally distributed, or like not normally, normally distributed. Right.
That's actually a very good question. We didn't try other kernels actually, and this is also, I forgot to mention that in the future direction. We don't have that much intuition about, like, let's say the shape of the kernel itself, how it impacts the gradient field, except that if you use the sigma parameter of this Gaussian, if you put it to like super small, you probably you get back to regular vanilla optimization. Except for this, we didn't like try to play with this other kernels, although that's a very interesting question. But I would be also interested in what happens if I use something different. I guess as long as the kernel itself is compactly supported, right? I guess you would expect still some kind of phenomenon like this one, like an extension on the whole space, but at the same time, the support wouldn't still be like non-zero everywhere. You just extend it a little bit. Now, if the kernel is not compactly supported, you might have more interesting phenomena. And the fact of also this question about using other losses. Yeah, this, especially if you use contradictory losses, like something try to reduce one thing and to increase something else, but I wonder what the interplay would be. This is also something we didn't try that much. Yeah, the losses we've used so far are really simple, as you pointed out, like just extend the sphere or destroy the circle or just extend the circle, like in this one. Now, it's likely that if you use more intricate or more complicated loss, yeah, the diffeomorphism itself might end up like more complicated. Actually, that's also something I didn't mention because I didn't show up the Lipschitz constant equation. I didn't show the explicit formula, but I think if you also have a more complicated loss, you also have a bigger Lipschitz constant, which means the diffeomorphic interpolation that you're making might be more complicated and also a bit harder to control if you have losses that are more complicated than just moving one point outside of the diagonal or towards the diagonal. So, in one word, my answer to your question is I don't know, but this is for sure interesting follow-up work, like trying to understand a bit better the interplay between the loss, the kernel, and the vector field itself.
Yeah, I don't know. No, thank you so much. Appreciate it.
All right, thanks.
Again, thanks a lot. Maybe a quick question towards the end. Otherwise, I'm going to stop the recording. Or does anyone still have a question for Mathieu?
If I may.
Of course.
Mathieu, thank you very much. It's very interesting. It's been a very interesting talk. Just a thought regarding optimizing the kernel bandwidth. Maybe, well, it seems to be complicated to do so purely analytically, but maybe you can try some stochastic approach, like sampling the sigma from some prior distribution, like something like an inverse gamma would be natural, and then estimating the gradient with respect to this parameter.
Interesting. So this distribution that you're mentioning would be computed out of the point cloud itself, I guess, and then I would sample sigma out of this.
No. I mean,
kernel?
but sigma is just one parameter, right? One number.
Right. Yeah.
So no, I mean, like, do it if you can't do it analytically, try doing it in a Monte Carlo fashion.
Okay, I see.
That's what.
Okay. So sorry, just so that I understand, do you mean that there might be some let's say some formulas or some methodology to actually pick this kernel bandwidth like in a more like precise way, quote unquote?
But I don't think so. But it seems to the optimal value of kernel bandwidth might be data dependent, right?
Yes, for sure. Yes.
So what I was thinking is that you try to estimate this optimal value in a stochastic manner. So you sample different values and then see if you get it better or worse.
Oh, I see. Yeah, great. I guess that would require a way to quantify if it's better or worse, but for sure, that would be a cleaner way to pick this bandwidth in a data dependent way.
But you have
go ahead.
Sorry to interrupt you, but
go ahead.
Have your topological optimization loss, right? So maybe that tells you what.
Yeah, for sure. Right. Yeah, I guess you could look at the loss and just use that as a let's say the referee. So as to be able to decide. But yeah, it would be cleaner for sure. At least having something, a bandwidth that's data dependent, I think would be a big improvement itself, probably.
That's a good closing sentence. So thank you once again, Mathieu.
Thank you. Thanks for everyone.